I'm Gil Rogers, and I'm a member of a group called the Minerva Action Group. And we're a group of about 8 people that are focused on climate change. But we have a specific position or attitude toward it. What we're trying to do is develop exercises, hands-on exercises that students can actually do to actually see and feel and smell climate change. Now, the one we're focusing on today has to do with carbon, or really CO2, carbon dioxide, that's captured in trees. So the exercise that we're doing is to actually measure a couple of species of trees, a northern red oak and a large maple. And we're doing different sizes of trees, large and small, to give you an understanding of how much carbon is captured by these trees of different sizes. We're at the Whitney Hill Park to actually do that with a number of my colleagues. Now, we use a little bit of geometry to do this calculation. We have to get certain measurements of the trees in order to do the estimate of the amount of mass of carbon that's actually captured in the trees. Here's the tree. For example, this might be the big oak tree that we measured. There's a concept in trigonometry, and those of you that have had plane geometry probably remember that, called the similar triangles theorem. And it says that if the angles of 2 triangles are the same, then the distances are proportional to each other. We measure with yardsticks the distance little a and little b, which is found by pointing a yardstick from an observer, one of my colleagues here, to the top of the tree, and then pointing the arm to the bottom of the tree. So that forms that angle. And then we measure these distances, little a and little b, and typically we do that in inches. And that's one of the things that's important about the exercise, is that we have to convert everything to the same units, which in this case is feet. Then the other dimension we need is the distance from the observer to the bottom of the tree. And that's this big A here. I mean, we have long tape measures that we use to actually measure that. The similar triangle theorem, it says that the ratio of the height of the tree, that's big B, to the distance, or big A, is proportional to the ratio of little b to little a. And then once we have that, those calculations, then we can solve that similar triangle theorem for the height B, which is what we're trying to get, the height of the tree. Why do we want the height of the tree? Well, what we're trying to do is calculate the volume or the mass of the tree. And to do that, we have to have a little bit of solid geometry where we model the tree as a cylinder or a cone. So for the 2 different types of trees, northern red oak and the maple tree, we have data that's been empirically developed by the Forestry Service to be able to calculate the mass of the tree. It depends on the density, depends on a number of things, but it depends on the volume of the tree. To get that, you have to have the circumference of the tree. You have to know what the base of the tree is. So the other thing we have to do is to go out and measure the circumference of the tree, and then from that, by simple trigonometry, we can get the diameter of the tree. And then from all of that, we can calculate what the mass of the tree is. So what you'll see in our exercise here is going out and making those measurements. Now, we're doing it for 2 different types of trees because the density, the amount of carbon that's captured in the tree varies based on the species of the tree. So that's why we use 2 trees. The other thing that's important about the exercise too is that the mass of the tree goes up not linearly with the height of the tree. It goes up as a quadratic, as a square of it, right? So that the thing is, when you do these calculations, you'll find the larger tree has a lot more carbon stored in it than the small tree. But that's why we choose different species of trees and different sizes of trees. So in our exercise here, we're going to do, for the 2 species, we're going to do a large tree, which is an older tree, and a smaller, younger tree. And then we'll compare the results from those 2 calculations. And that'll give you an understanding of the amount of carbon that's actually been captured in these trees. So that's one of the exercises. We've done it a number of times in different locations, and it's a pleasure to be doing it here in Watertown because of this beautiful forest area.